This video covers the energy page of the ACEP Premium Access portal. The page presents the spacecraft energy system as a closed physical chain, spanning Disimcoffer reactor, waste heat generation, thermoelectric conversion, thermal rejection, electrical storage, and power distribution. This structure allows the complete energy balance of the spacecraft to be examined as a single, continuous process, evolving along the mission timeline. The Energy State Panel presents a normalized, time-resolved view of the spacecraft energy system. All traces represent utilization or state ratios expressed as percentages, allowing heterogeneous subsystems to be evaluated within a single reference frame. The panel includes reactor core load, thermoelectric generator utilization, MHCS system utilization, electrical bus loading, storage state of health, auxiliary generation contribution, power distribution controller lane share, and the heat-to-energy conversion fraction. Displayed together, these traces define the instantaneous operating regime of the energy system, with stable regimes producing characteristic, repeatable patterns, and transitions appearing as coordinated shifts across multiple utilization curves. The UVIRSA and UPS-SSB panel presents the spacecraft's external solar generation and electrical energy storage systems. UVIRSA, representing the ultraviolet and infrared solar arrays, remains inactive during interstellar cruise and becomes operational only after arrival, when stellar irradiance permits sustained power generation. UPS-SSB represents the solid-state battery packs, which are maintained near full charge throughout the mission and provide buffered electrical supply. Prior to arrival, this panel is primarily used to monitor component health, with gradual degradation indicated by gray attenuation within the graphical fills. After arrival, the panel transitions to an operational power view, showing UVIRSA electrical output in relation to UPS-SSB charge level, allowing direct assessment of generation, storage, and long-term sustainability. The Heat Radiators panel presents the spacecraft's thermal rejection system. The left section shows the instantaneous state of individual radiator panels, with active units displaying average surface temperature in Kelvin. Color intensity represents thermal loading. The right plot combines radiator utilization and radiator temperature over mission time, with utilization expressed as percentage of available radiative capacity and temperature plotted in Kelvin on a secondary axis. A separate trace shows the total required radiative fraction, allowing direct comparison between heat rejection demand and active radiator capacity. This panel is used to track thermal margin, verify staged radiator deactivation, and confirm that remaining active radiators operate within nominal temperature limits. The Thermoelectric diagram panel presents a complete real-time topology of the spacecraft thermal and electrical energy system. The panel is implemented as a schematic system map, integrating summary frames, hardware units, transport paths, and loads into a single, unified representation. Two general summary frames provide an at-a-glance representation of the global energy state. These frames aggregate system-level thermal balance and electrical balance parameters. Individual subsystems are represented as discrete hardware units, including reactor cores, thermoelectric generators, batteries, power buses, and auxiliary systems. Each hardware unit is enclosed within a state-coded frame, where green denotes nominal operational status, gray denotes inactive or out-of-service state, and red denotes a fault, limit, or non-nominal condition. Electrical loads are displayed as enumerated lists associated with their respective power buses, with each entry reporting instantaneous power draw. Thermal transport is represented through phase change material circulation. PCM reservoirs indicate continuous thermal transport loops operating between heat sources, converters, and sinks. System connectivity is defined using 4 distinct line types. Yellow dashed lines represent electrical connections. When inactive, these connections are shown in gray. When active, animated dash motion indicates the direction of electrical power flow, and each segment is labeled for identification. Red dashed lines represent hot PCM transport paths. Inactive segments are shown in gray, while active segments display animated flow in the direction of heat transfer, with utilization reported per segment. Blue dashed lines represent cooled PCM return paths, completing the thermal loop following heat extraction or radiative rejection. Dark purple lines represent ceramic bridge links, providing direct thermal coupling from the metallic hydrogen combustion system to selected thermoelectric generator units. Inactive ceramic links are displayed in gray. Waste heat is a direct byproduct of the fusion process and represents a fraction of total reactor plant power. This waste heat originates at the 2 DSIM-4 reactor cores, 1 and 2, each representing a complete reactor assembly comprising the fusion chamber, superconducting coil systems, diverters, cryogenic infrastructure, and all mechanically and thermally coupled auxiliary subunits. Reported plant power includes fusion power output and the internal power demand of core-attached systems, including magnetic confinement hardware, diverter handling, cryogenic support, and fuel storage conditioning, excluding electronic control and external avionics loads. Each core block reports instantaneous plant power, diversion throttle, and the corresponding waste heat flow routed to the thermal management system, shown as heat to HC1 for core 1 and heat to HC2 for core 2. Superconducting coil array readouts report maximum HTS temperature, quench margin, and cryogenic utilization, defining the electromagnetic and cryogenic operating envelope under current load. Waste heat is collected into hot circuit 1 and hot circuit 2, forming the primary waste heat collection and transport loops. Each hot circuit reports ring average temperature, heat input, heat output, and net thermal balance, defining the instantaneous state of waste heat transport, buffering, and circulation. Thermoelectric energy conversion is performed by 3 thermoelectric generator units, TEG-1, TEG-2, and TEG-3, coupled to the reactor waste heat system. The TEGs extract a controlled fraction of thermal power from the hot circuits and convert it directly into electrical power, which is routed to the power distribution controller. TEG-1 is a low-power unit rated at 20 kilowatts electrical output. It operates only during the pre-midpoint acceleration phase, when waste heat availability is highest, and is permanently taken out of service after the mission midpoint. TEG-2 and TEG-3 are higher capacity units, each rated at 40 kilowatts electrical output. They remain operational through the midpoint, the deceleration phase, and post-reactor operations. Each TEG reports thermal input power, electrical output power, and utilization, allowing direct assessment of conversion efficiency and loading. After reactor shutdown, or when reactor waste heat becomes insufficient relative to electrical demand, thermal input to the TEGs can be supplemented by the metallic hydrogen combustion system, MHCS. MHCS is a dedicated auxiliary thermal generator that converts stored metallic hydrogen into controlled thermal output via regulated exothermic recombination. The generated thermal power is transferred through ceramic thermal bridges directly into TEG-2 and TEG-3, bypassing the reactor hot circuits and providing a stable, reactor-independent heat source for thermoelectric conversion. MHCS operation is optimized for low to moderate power regimes, enabling sustained electrical generation during post-reactor operation, arrival phase activities, and long-duration hibernation, without reliance on fusion-derived waste heat. Engagement level, thermal output, and coupling to individual TEG units are autonomously managed by ORI to meet electrical demand while minimizing metallic hydrogen consumption and thermal cycling stress. Electrical power produced by the thermoelectric conversion chain is aggregated and dispatched by the Power Distribution Controller, PDC. The PDC functions as the central electrical routing, protection, and authority node, interfacing electrical generation sources, storage systems, and downstream power buses. The PDC reports instantaneous electrical power input, electrical power output, net balance, and available headroom. It additionally exposes ORI-controlled routing state, including active distribution lanes, lane share, UPS-SSB charge or discharge flow, external input status, and degradation flags. Triple redundant distribution lanes, labeled A, B, and C, operate in parallel with continuous cross-monitoring. Lane share percentages indicate the real-time distribution of electrical flow across the active lanes. Electrical output from the PDC is routed to 3 primary buses: main bus, aux bus, and MADS bus. The main bus supplies continuous core spacecraft functions, including ORI hardware, navigation systems, sensors, and primary avionics. It reports instantaneous load, utilization relative to rated capacity, and remaining headroom. The aux bus supplies secondary and intermittent subsystems, including communication emitters, fuel system control electronics, Atmos probe charging, and auxiliary controllers. The MADS bus supplies the microwave active debris shield system and represents the dominant electrical load prior to mid-cruise inertial reorientation. Electrical loads are displayed as enumerated lists attached to their respective buses, with each entry reporting instantaneous power draw, allowing direct attribution of electrical consumption. Through this structure, the PDC and bus topology define how much thermally generated electrical power is absorbed by spacecraft systems, and consequently, how reactor waste heat is partitioned between electrical conversion and direct thermal rejection. UVIRSA and UPS-SSB together constitute the spacecraft's post-reactor and long-duration electrical power subsystem. UVIRSA consists of 2 independent ultraviolet infrared solar array units that provide external electrical generation after arrival in the Proxima system, once stellar irradiance is sufficient for sustained operation. Each array delivers a per-unit peak electrical output on the order of 120 watts under design irradiance conditions. Output is monitored via utilization and degradation metrics, with gradual capacity decline driven by radiation exposure and material aging. UPS-SSB comprises 2 solid-state battery packs that provide electrical energy storage and buffering. Each pack has a nominal capacity of approximately 500 watt-hours, with defined charge and discharge limits and continuous state-of-health monitoring optimized for multi-decade operation. Both units operate in charge or discharge mode, absorbing excess electrical power when generation exceeds demand and supplying power when generation is insufficient. After reactor shutdown, UVIRSA and solid-state batteries operate as a coupled system, with UVIRSA providing continuous low-level generation and UPS-SSB stabilizing bus voltage and load transients. During early post-reactor and arrival phase operations, electrical generation may be supplemented by MHCS-driven thermoelectric conversion, reducing battery discharge rates and preserving long-term storage margins. Charge-discharge scheduling, operating mode selection, and interaction with PDC routing are autonomously managed by ORI to maintain electrical balance, minimize battery cycling stress, and maximize system longevity. Thermal radiators provide primary rejection of reactor-generated waste heat. The system comprises 3 independent radiator units, each rejecting thermal power transported by the phase change material loops. Each radiator reports radiated power, utilization relative to rated capacity, and average temperature in Kelvin. Utilization expresses the fraction of available radiative capacity required for thermal equilibrium. Average temperature characterizes the operating state of the active radiator surfaces. Radiator operation is staged. As waste heat load decreases over the mission, lower priority radiators are taken out of service. This concentrates heat rejection on the remaining active units and preserves efficient operating temperatures. Radiator status, load, and temperature define thermal rejection margin and constrain waste heat partitioning between electrical conversion and radiative rejection. The magnetic nozzle contributes secondary thermal load, returning plasma and coil dissipation heat to the hot PCM circuit. Thermal energy is generated by resistive losses in the superconducting coil array and by intercepted plasma and field-shaping loads during thrust and vectoring operations. The nozzle is therefore cooled by PCM circulation, with cold PCM entering the coil structure and heated PCM routed into hot circuit 2. The nozzle telemetry reports HTS temperature, quench margin, cryogenic utilization, and the resulting thermal power returned to the hot circuit. This configuration routes propulsion-related thermal losses into the same thermoelectric and radiative infrastructure as reactor waste heat, preserving closure of the spacecraft energy balance. Together, the energy page provides a closed, end-to-end view of thermal generation, electrical conversion, storage, distribution, and heat rejection across all mission phases.